Greetings everyone. We have just completed the course on semiconductor basics of semiconductor processing and IC fabrication. While we have had a lot of discussion on various topics, today I'd like to give a brief supplementary lecture. This would be based on an alternate way of making thin films. This is as an example just to tell you that there may be other ways of doing stuff than the mainstream method. So let's get started. I'll be talking about the printing process for thin films. The disclaimer. So this is the preamble of what I am intending in this lecture. The VLSI processing, we must remember, is the forerunner of today's semiconductor processing. It's the mainstream process. If you want to make ICs, all the different stuff that we discussed, especially the unit processes, those are the topics that usually will keep repeating and you will use it for various types of materials. Now, that being said, there are many alternate strands in processing that are extant or that are available today, and often these are for niche application. To give an example, you can talk about flexible electronics, maybe for displays. So there are certain types of applications where you may go a little different from the traditional VLSI processing that we discussed. So these may be appropriate and maybe more economical for that particular type of fabrication and for those devices. May not be applicable for VLSI often. Printing and coating of thin films is one of the example of one such offbeat or different types of forming thin films. Sometimes they could make their way into mainstream technology as well. Okay, so for example, coating photoresist. Spin coating is one of the methods. It's a coating method, remember that. But maybe one can also go for slot die coating if you have a large area. And indeed, people do use these in some instances where you want to get high throughput. Now, here we take a peek into printing and coating processing of thin films. So this is the outline of what I am intending to cover discuss in this lecture. First, I will talk about the motivation. Why do we need to look at printing? Okay, what is so special and what is different about it? And also the introduction to printed electronics, especially I'll be talking about the processing part. I won't be talking about the applications. Then I will talk about some of the printers that you could use, the aspects of inks we have to keep in mind, and the post-printing treatment. So let's get started with motivation and introduction to printing of electronics. Printing electronics, actually it involves two different vastly divergent fields. First, it talks about printing, something that started in the previous millennium, more than 1500 years ago. And then of course around Gutenberg press is when the printing the way that we know about became more common, and that's when books and other things started getting published. And especially in the last 200 years, a lot of progress has happened, and so this is a very well established technology. And of course you have electronics, which we discussed as well. We saw that around late 19th century and especially early 20th century is when we can say electronics sort of started. And the last 100 years or so, it has really changed life, and it has evolved and become very sophisticated technology. So two sophisticated technology, we want to bring them together. Just to show the apparent incompatibility as it might appear to somebody, print shop floor, if you look at it, as per what your modern IC fabs is maybe considered to be dirty. You don't want things to be done in a shop floor. On the other hand, modern IC fabs has to be pristine, very clean. You want to make sure there are no dust particles and so on. So are they compatible at all? Well, in some instances you can bring them together. But before that, why do you want to bring them together? That has to be clear. There are lots of good reasons why you want to bring them together, as we will be seeing in the next couple of, at least we'll see a couple of reasons. And yes, the combination is a reality today. There are lots of things that are being printed, including in mainstream technology, as I will be giving at least one example. So comparison with traditional process, especially what we spent time discussing in the last 2.5 months to 3 months. This is the traditional processing. You might remember, you prepare the substrate, then you have an addition of a layer, then you do patterning, and then you remove the material from the places where you don't want, and then you remove the resist, and finally you have the patterned substrate where you have patterned processing, in the sense it could be a growth of a thin film, or it could be implantation in those regions, whatever it be. So what you are doing is you are going addition, patterning, subtraction. If you look at printing, you just come in and put the material only where you want. See, it's a direct addition of the film to form the pattern. You can immediately see there is a big difference in the whole approach. Of course, usually printing happens at very low temperatures and room temperatures typically. This happens at high temperatures. So the whole chemistry and the approach may be different, but it may not be that always you need to go to high temperatures. So if you look at it, printing is a purely additive process because there is no need to subtract. You do the patterning earlier itself, and then you deposit only where you want. And you can see, you can argue it's much simpler. The very fact that you have only one process, probably you do all the thinking of where you want to put before you put it. So maybe that's what our parents would tell, plan before you do stuff, right? So maybe printing does that to a greater extent. Maybe it's possible for printing to do. It's not that the other process doesn't want to do it. Maybe it's not possible to do in the other case. So printing is a simpler process, less processing step, and hence it can be potentially very cheap, assuming you are able to get the material, the inks and all that to behave the way you want. It helps wastage because it's not that you dump something and then you clean. It's not as though you dump dust in your room and then you clean it. You don't dump dust in your room in the first place to keep it clean. That's the way to do, right? So you have less wastage here. So there's no question of runoff and all that. It will be much less, at least. Inbuilt information of where to deposit is there in the process itself, and hence there is no lithography step needed. And if you might remember, lithography was one of the crucial steps, and that's where often the rate was limited, at the rate at which you could do the production, because you have to step from die to die to die, and also you have to have fine resolutions. Maybe printing cannot give you that resolution, but wherever it can, printing will be faster and environment friendly from many ways. The amount of energy needed, first of all, is done at low temperatures, but that takes away a lot of possibilities. But wherever you can, you don't have to take it to high temperatures, and you don't put stuff and remove, so environmentally very benign. That being said, let's see where printing lies in the phase space. So before that, we can see printing can be done sheet to sheet. The common expression way they write that is S to S. That means sheet to sheet. This can be done, this printing can be done on rigid substrates. It can be done on flexible substrates also. But there is another method of printing, which is roll to roll. This is very popular, especially if you have flexible substrates, say paper, cloth, steel, plastics. So these can be done roll to roll. So the whole approach is, as you can see, is a little different. And for printing, and here I am being little sloppy in terms of rigor by including sometimes coating within printing. Okay, some of the coating printing main difference is coating patterning is much less, but there are lots of coating processes. You can get some basic patterns that you need as you are coating as well. So I am clubbing them a little together. So roll to roll process, when you are doing, you can go several meters per second in the linear direction. So area wise, you will have several square meters per second being printed in one go. In the linear direction, velocity is 10 meters per second. And this picture, I think, speaks volumes. Here they are trying to print some solar cells, and you can see this huge machine, and this man standing nearby gives an idea of the size of this substrate that is getting printed. And this, even if it is not several meters per second, you can see within one day you will have several square meters of electronics with you. So clearly this will be much faster if you are able to do what you want with this process. I am always adding that caveat if, because many things you cannot do with printing, what you can do with conventional technology. Otherwise everybody would have done printing, right? But wherever you can, printing does give you an edge in this aspect. So you can see it's a very high throughput. And one of the ways in which they compare it is the area of electronics by conventional electronics today. If you look at it, in 1 year what you will produce, it's several tens of thousands of square meters of electronics, but sometimes you need some square kilometers of electronics. For example, if you want to deploy photovoltaic technology, if you want to deploy, you need several square kilometers. So there you need processes like printing, right? So here the area of printed electronics that is made in 1 week will be equivalent to what you do in 1 year by regular electronics. So throughput, if you get the right process that you desire, can be much higher by printing, especially roll-to-roll printing. Just want to put a note here, roll-to-roll vacuum process is also available, okay? There are technologies where they use roll-to-roll vacuum process, but this roll-to-roll vacuum process could have, besides additive process, could have a subtractive process as well. Etching also could be done as it is going through. Lithography also could be done. Pattern could also be done as going through. If, of course, depending on all that, the rate at which you can do will be lower. Now, but we are here talking about direct deployment of thin films, often at room temperatures or slightly elevated temperatures. So let's see the trade-off of throughput and resolution, which is one of the Achilles heel, if you want to say, of the printing technology. If you look at lithography, you have the very small feature sizes you can get. We know that we are getting almost nanometer size or a few nanometer size lithography you can get, correct? On the other hand, printing, the feature sizes are much bigger. If you really push the limit, you come to around 10 micron as the line width, okay? But on the other hand, if you look at the area per second that you can produce, in the linear dimension it is tens of up to 10 meters per second or few 10 meters per second you can get. So that means if you have 1 meter website, the web length width is 1 meter, you will have 10 square meters made in per second, right? So you have several square meters and several tens of square meters you can make by various processes. Offset, gravure, flexography. Offset is what you use for your newspapers. Inkjet, you can even have laser ablation, all these laser printing, if you want to call it that way, but then the laser printing throughput is lower. So throughput may be high, but resolution is where you get the hit. That's why scaling issues may be a challenge. So you cannot use printing for all aspects of our current VLSI technology the way we use it. So wherever resolution is not an issue, and I would want to add a caveat here, you are able to do it at the temperatures under the conditions that you want, maybe printing is a good method. I also want to show you an example where printing is actually used. If you look at photovoltaic technology, silicon technology is one of the mainstream and mainstay of photovoltaic technology. Most of the processing is done similar to the processes we discussed. Diffusion, implantation, etching, all those can be, you may find their way into that. Junctions that you make for photovoltaic process or deposition of polysilicon and so on. But when they make the metal contacts, very often, and since metals could be deposited at lower temperatures and you just need to have a small anneal following it, you actually often end up making metals by printing. Very often in many of the devices you will have silver at the top, silver patterns, okay, silver mesh that will be there at the top, that will be screen printed. On the back side, in some cases you may have aluminum, that also could be printed, and that could be, it's a slot die because there is often not much of a patterning there. But even if you have a double-sided solar cell, even the backside could also be screen printed. And silver is often the metal that is used because silver has very high conductivity, very low resistivity. So that's why you use silver. But because silver is costly and when you can afford to make it thick and wide area, you use aluminium. So the mesh on the top in this particular solar cell example I am giving, and there are almost all the solar cells that we use in commercially, the metals are printed, screen printed using silver, often silver nanoparticle based inks or nanorod based inks are used. The bottom electrode can be aluminium, and which can also be printed or coated on the solar cells. Double-sided solar cells may have mesh on both sides, as I mentioned, and that's becoming increasingly popular because the reflected light from the ground also is being collected in the photovoltaics. So this is an practical example of semiconductor processing where you do use semiconductor device processing, where you do use printing. The printing production process, if you look at it, it can be summarized in this manner. To get an overview, two things are needed to start with. First, you need the substrate, and you may have to prepare the substrate, do whatever you need, and then you have the ink. These two together, you will want to dispense it, and this is where the printing or the coating method comes in. And once this is done, you do the post dispensing treatment. Often you have to do some drying, sintering, curing or annealing depending on what you want. And then once that is done, the layer is formed as you desire. So a lot of chemistry and lot of physics and chemical engineering and all that is involved in this. Now once you do one film, you can iterate the sequence to make the complete device. Device is essentially a combination of thin films in many situations. Now if you look at it, innovation in ink is the key. If you look at it, the ink is the key aspect, okay? And of course, substrate preparation depending on what substrate you are using. As we saw even in silicon, the cleaning of the substrate, which we discussed in the etch unit process, is very critical. So similarly, substrate also has to be prepared. Sometimes you may have to expose it to a plasma so that it becomes, films can adhere to it better. Then there's a lot of innovation in the coating methods, and this is what probably we see. The printers is what we see, even in just like our regular printing, even in electronics, the printers is what we often talk about. And then post dispensing also is a very important aspect. This is where the dispensed liquid transforms into the thin film that you desire. So the drying techniques are tried, and metrology is needed because here the volumes are much larger. It's not just small dye, small area. You're talking of several square centimeters at least, but clearly several square meters in many situations. So materials dispensed only where it is needed, and that's one aspect of this whole process. So there is no lithography as such. Now let's move to discussing about printers, ink and post processing, and just take a bird's eye view of what it is in this interesting approach of dispensing and forming thin films. Printing electronics, usually you can use any printer that you have for your regular printing on paper, for reading, writing and images and so on. In theory, any of them can be used for printing electronics as well. You just have to use the right ink and you have to tune the printer such that it dispenses it properly. Here I have given a couple of examples. A Dymatex printer, which is an inkjet printer with 16 nozzles, and this is a slot die coater. And in fact, many of the labs have a variety of these printers. The labs at IIT Kanpur has a variety of printers. Those who are interested can check out the website. So these are all what you call sheet to sheet process. So typically a sheet, maybe an A4 sheet, you put it in, it prints whatever electronic pattern that you want. It can be paper, it can be cloth, it can be plastic. Often plastic is used. It can even be glass. A glass sheet can be put in and it will print on glass. Another method would be the roll to roll, as we discussed. Here you should be able to bring the material continuously, almost continuously during the time of printing. That means you should be able to have the substrate in the form of a roll. Now, when you have that, you can have very high throughputs. So, variety of printing process may be adopted, and I put a star here just to reiterate the point. Experts in the field of printing will balk when I say that slot die coating is printing. Okay, but I guess we understand what we are talking about. So they are strictly coaters, or they are coating a film, because they don't go around making patterns. But that being said, you can actually make sure that you can have strips being printed. You can lift the print head so that up to a point something is printed. So, but the patterning capacity is lower. They are usually useful for making big electrodes, or for solar cell applications and so on, where you talk about a large area of electronics. So, you can make inkjet, gravure, offset, flexography, screen printing, slot die coating, and you name it. There are many, many more. And high throughput with R2R process and several meters per second in the linear direction is potentially achievable. I must put a word of caution here. Newspapers print at tens of meters per second, and that's because you need so many newspapers to be distributed across the city, right? But that's because the process is also very well understood. So you have only limited options of what you are wanting to print in terms of the material property. So that being said, and also the characters of the letters, if you are talking of books, only so many combinations, right? So that being said, even electronics can be printed fast, but usually you can do that only after the whole process is very well studied and you have the whole process under control. Then you can afford to slowly increase the throughput. Otherwise, if there is an error, a whole amount of ink will go waste. The error will also propagate very fast, right? So you have to go very carefully. So usually in development, research and development, you go a little slow in terms of the speed at which you print. But in actual manufacturing, once the process is stabilized, you can go to several meters and higher. Usually when you go to higher speed, the certain properties become more difficult to control. Methods of printing, let's take a quick overview of some of them. This is the flexo printing. This is like a rubber stamp. You can see this plate, there are projections that are above. So the projections will pick up the ink from this roller, and then it will dispense it on the impression cylinder, and the substrate is wrapped around the impression cylinder. So this is flexography printing. Okay. You can also have the opposite. If you can have something sticking up, you can also make grooves on it. As you can see, there are grooves on this. So the ink is dispensed. The ink is just filling the grooves. Because of surface tension, only the grooves get filled. And when this substrate touches this, the ink is coming from here, it is filled with the grooves, and once it touches it, whatever is in the groove gets transferred to the substrate because of surface energy minimization, and then it goes on. So whatever pattern is there as a form, in the form of a groove, is what is transferred onto the substrate. This is actually a very high quality printing. Usually magazines are all printed by this. Same technology can be used for printing finer resolution and electronics as well. Flexo, on the other hand, usually is not such a high resolution, because when you press it, the ink can spread. Of course, they use tricks by using rollers and things like that, but that's how it is. Then there is offset printing. If you have something elevated, something depressed, you can also have something on the same level. Here you play with chemistry. So something is hydrophobic, some regions are hydrophilic in that drum where the pattern is made. So when it touches the ink, the hydrophilic regions will have the inks clinging to it, hydrophobic regions will not have any inks clinging to it, and then through rollers you can transfer that onto the substrate. So now, what ends up happening is newspaper printing often uses this. One advantage is the patterned drum is not actually searching the substrate. The ink is transferred to another drum and then it goes to the substrate. That's why it's offset, they call it. Now, because that is done, the drums can last for a long time, and newspaper printing often is used with that because it can you can print a large volume of them in one go. Then there is screen printing. It's possible some of you have indulged in this when you are printing some design on your t-shirt. You have a web, and through the web, you with a squeegee, you press the ink underneath on it, and the ink goes underneath and sticks to the substrate. And then you have inkjet printing. Okay, so inkjet printing, originally they used to have continuous drops. They'll charge the drops and try to deflect whichever shouldn't go to the substrate. It will go to the drain. But more recently, and since the time many of us have been using it in our offices or homes, inkjet printing, there is something called bubble jet. You might have heard. It's a thermal process where by heating the air pocket, you increase the pressure and dispense the liquid. So wherever you want to dispense, you heat the bubble, ink gets dispensed, then you cool it, then it doesn't get dispensed. Or you can have piezoelectric approach, where you apply a bias, the pressure changes, and so ink is dispensed. And then when you don't want to change the bias, so the pressure reduces, so the ink is no longer dispensed. So this is a print on demand type inkjets. Then you have slot die coating, where you have a doctor blade, you dispense a film and you just make sure that a thin film is remaining. And you have many others, wire bar coating, knife edge coating, and so on. Many other coating methods are also there. Typically in all this, different things will have different types of ink. As you can imagine, screen printing will have something like toothpaste, right? Something viscosity will be very, very high. It will be like toothpaste. You have to press it and it goes through the openings in the screen and gets printed. On the other hand, something like slot die or gravure and all, this will be like honey, right? It will just stick to it. And then you will have inkjet, which has to be more watery because it has to flow. So you actually play with the viscosity and the solvent and all, and you are able to develop the ink. We'll touch upon that a little later in a couple of minutes. Now I have just given a snapshot. Actually, there is you can use, as I said, anything that you use for regular printing, you can use it for electronic printing also. Maybe block printing also. I don't know how fast that would be, but you could use that. Okay. Now, target property of the layers printed. The material that is formed in our traditional printing, which we have for books and magazines and pamphlets and so on, usually we talk about colors. In the black and white age, there were two colors, black and no color, that is white. Okay, so you will not print it there. So wherever you are printing, it will be black. But sometimes you have three colors, you can mix and match. And in the world of inks, cyan, magenta, and yellow are the primary ink colors. So you mix them, you get black. In light, red, green, blue, if you mix them, you get white, right? So here it's the complement world. So three primary colors are there, and you can decide to print how much of what ink where to get the appropriate color at a place. So you need to print these colors, and patterns are generated, and you can see that various colors are printed in this by playing around with the basic colors. Okay. On the world of printable electronics though, it won't be colors. We print electrical and optical properties. You can see that electrical, you have insulator, semiconductor, conductor. So you have inks should be bringing that property when they dry and form the layer. If it's an optical property, you need to be transparent, or it should be responding to light, and so on. It should have a fluorescence. That type of property should come to the film. So and often many times you even have barrier layers, which are chemical barriers, or maybe barriers to electrical or optical or electric charge or optical energy. It could be emissive, absorbent, or transparent. So these are you can see that it's very similar to traditional printing, except that what we are looking for in the film is different. So you'll have to use the appropriate chemicals. The overall process, in a way, at the high level is very similar. To give an example, I have shown maybe an organic solar cell that is being printed, organic solar, where all layers are being printed. So what you can do is, the bottom layer is an encapsulation layer. So it should not allow any moisture or something to go through, and every layer in this should have the appropriate property according to what is needed. For example, the electrode should conduct well. If it is at the top, it should also be transparent, and so on. So here you can print different layers, and combining them you can make a device. As we saw, ink is the key. Okay, here I am showing some of the inks developed at IIT Kanpur's Flexible Electronics Center. Here they have developed conducting ink as well as insulating ink, and in conducting ink they have silver as well as copper. Copper also is a good conductor, but copper oxidizes. Silver, of course, is better conductor. Now, the properties that you have when you are conducting, insulating, semiconducting, and barrier coating. So you choose these with the molecules that are part of the basic ink that you are using, molecules, and then you combine them together to have certain material properties. But then you need to be able to dispense it as per the printer, and we saw that according to the printer the viscosity will change. So you add solvents and so on, and you play with it to get the right viscosity. Then you also need to add in that thing binders as well as solvents, so that they spread out and they bind to the surfaces that you want them to bind. A lot of chemistry involved here. And then you sometimes put additives to make sure that they smoothen out, they dissolve better, and so on. Better material thin film properties improve. So you can actually play with the ink, and there's a lot of research that goes on. And then, of course, finally you compare it with regular devices once they are done. Once the printing is done, we need to have some post-dispensing treatment. So clearly, it cannot be in a liquid form. It has been dispensed. You want it to convert into solid. Of course, drying would be the natural thing, dry away the solvents. But many times when it is being printed, the original form that you are using may not be having the properties that you want. So the properties that you want in the thin film often comes because of the subsequent process, the post-dispensing process. So you can have curing, for example. Curing is when there is a chemical reaction that takes place and maybe the molecules combine with each other, like vulcanization of rubber is one of the popular examples they give for curing. So it's a chemical process. Or you can have sintering. Lots of nanoparticles of metals are there, they come together, and without going to the melting temperature, they coalesce together and form a continuous film. And then, of course, the all-encompassing annealing is there. So annealing is a heat treatment which changes the physical and sometimes even the chemical properties of the materials and increases the ductility and reduces it to make it workable for what you want. Okay, and this annealing process requires material to go above what is known as the recrystallization temperature for the material, and then you bring it below that. So annealing is a specialized thing, and that's a more generic method that can be done. So what it means is, depending on what you are doing, you may have to choose drying, curing, and sintering and annealing. Now, many of these processes require temperature. If temperature is the thing, how do you handle that? Because you have sheets in which the films are formed, so you have to have, you can heat the surface with conduction. That is, you can have hot air flowing. Conduction is the web itself, where it can go over a drum which can be heated up. So that's one way. Convection is hot air can be directed to that so as to heat it up. Then, of course, the modern methods which are more surgical in a sense, you can have radiation. You can have microwaves to just heat the liquid that you want, or infrared or ultraviolet. Sometimes even X-rays could be used. So radiation could also be used for achieving this drying, curing, sintering, and or annealing, whatever you need to get the appropriate property. Now, once it is dispensed, the final subfilm could have various defects. You have to make sure they are avoided, and this is the typical process challenge, similar to what we studied in various thin film processes and other things. You want to get a dielectric layer, so it's clearly metallic metallic contamination should be there. So if it is a dielectric layer that we are trying to make, there should not be any pinholes, because if I put a metal on the top and the bottom there is conduction, the pinholes may end up having a metal going through and it will conduct. There should not be any cracks. There should not be any variability, because if it is varying, then the property also varies. There should not be any contamination in terms of particulates. When we discuss that, you have to remove that. So here it's a bigger, different type of challenge. The whole big substrate should be removed of all these contaminants. So we need to avoid these in order to make sure we get good quality film. So that was a bird's eye view. So let's see what are the takeaways. Printing process to form thin films is practical and often viable. Okay, only additive step is needed, lower cost, eco-friendly. Of course, there may be constraints as well. You may not be able to go to high temperatures, for example, but you can get very high throughput if you can adopt it. Usually you adopt it wherever your resolution is not so critical, because lithography is certainly far superior in terms of the finer resolutions that you want. But many things you don't want that fine resolution. So there we can, why not, instead of using lithography, why not use printing? A variety of printing techniques may be adopted, as we have seen, and they broadly come in two categories: sheet to sheet or roll to roll. If you are doing some wafers, maybe sheet to sheet approach might work, and roll to roll in case you are using large substrates, say flexible substrates. Ink formulation actually is the trick in the whole printing process. If you look at it, lot of sophistication will go into ink processing, of course in conjunction with the design of the printer and post processing and all that. Post processing is what leads to the desired property. So if you look at the precursor, it may not have many of the properties that you are wanting in thin film, but by doing printing and dispensing it, forming thin films and processing it, you may end up getting the appropriate properties. So with that, I conclude this discussion, and those who are interested, I'll welcome you to look at these two references. Professor Steve Abbott has put a lot of material on the web, and he has a lot of publications as well, books and so on. You are welcome to check that out, especially in the domain of printing. It may be generic printing, but remember that the inks, when you are able to get, the printing process will be similar, the processing will be similar. So Handbook of Print Media is also an excellent book, very exhaustive, and this is something that those interested can refer to it. Maybe you can get one for your library, because as being a handbook, it's on the costly side, but it's a good book, very good book. So with that, I conclude this supplementary lecture on printing, which was just to highlight that there may be other ways of processing, including processing of semiconductors or processing on semiconductors, whichever way you want to look at it. So, so you should keep your eyes and ears open. Okay. With that, I conclude this discussion. Thank you. It was great to be part of this whole exercise, and I'm glad I was able to share whatever little I knew, and whatever I knew actually is because of my teachers and many of my colleagues and students from whom I learned a lot, and of course all the textbooks and publications and all that we have had a chance to go through. So I hope you will also make use of all the resources and use it for something productive. Wish you all the best.